In this third part of the turbomachinery chapter, we will cover 17 more slides of the lecture notes. Let's start discussing the details of centrifugal pumps. This figure, taken from Munson's book, shows two different views of a centrifugal pump. Important parts of it are the outer casing, also known as the volute, the impeller disc, which is attached to the shaft and rotates with it, and the blades that are attached to the impeller disc. Flow enters the pump parallel to the shaft axis from the opening known as the eye. Inlet side of the pump is also known as the suction side. Flow exits the pump perpendicular to the shaft. Outlet of the pump is called the discharge side. The pump's main job is to create a pressure difference between its inlet and outlet while moving the fluid at a certain flow rate. As the blades rotate, the fluid between them is pushed radially outward into the volute opening. The size of the volute opening increases in the flow direction to keep the flow speed as constant as possible. This is what a centrifugal pump looks like from the outside. The spiral-shaped volute is easily recognized. The blue part is the electric motor used to rotate the shaft. This is a single suction type centrifugal pump. Fluid enters into the blades only from one side, and the other side of the blades is closed. On YouTube, you can find several videos explaining the working principle of centrifugal pumps. The ones listed here are only a few samples. Please watch a couple of these or similar ones that you're going to find yourself. The pump shown in the previous slide had backward curved blades. Blades are called backward curved, radial, or forward curved, based on their curvature with respect to the rotation direction. The most common type is backward curved, where the blades are curved opposite to the flow direction. If the blades are straight with no curvature, they are called radial blades. Blades can be open or shrouded. Open blades have an impeller disc on one side, or they may have no impeller disc at all. Shrouded blades are closed from both sides. Here you see a number of different impeller and blade designs. Note that the blades of a centrifugal pump are also called vanes. This design, for example, has no impeller disc. Both sides of the blades are open. If the blades rotate in this direction, it is called a backward curved design. If they rotate in the other way, it becomes a forward curved design. Here we see a comparison of single suction and double suction type centrifugal pumps. In the single suction type, the fluid enters the space between the blades only from one side. There is only a single eye opening. The inlet and the outlet are parallel and perpendicular to the shaft, respectively. In the double suction type, flow enters the space between the blades from both sides. There are two eye openings. Both the inlet and the outlet of this pump are perpendicular to the shaft. Centrifugal pumps can be single-stage or multi-stage. In a multi-stage pump, several impellers are attached to the same shaft. The flow exiting the first stage goes into the eye of the second stage, and the flow exiting the second stage goes into the eye of the third stage, and so on. A multi-stage pump is similar to several single-stage pumps connected in series. It is used to generate a high pressure difference, in other words, a high total pump head. In certain centrifugal pumps, typically the larger ones, there can be stationary diffuser vanes. Fluid that comes out of the rotating impeller blades go in between these fixed diffuser vanes. The aim is to have a more controlled expansion of the flow area, a more controlled decrease in velocity, and therefore a more controlled increase of pressure, resulting in a more efficient pump. Pump head is one of the most important parameters of a pump. Its physical meaning can be seen by writing a Bernoulli equation between the inlet and outlet of the pump, in other words, between the suction and discharge of it. Bernoulli equation has the total head at the inlet the total head at the outlet, and the pump head. Pump head is shown here as HS, with S denoting shaft. It can also be shown with HP, P denoting the pump, or with just H with no subscript. According to this Bernoulli equation, pump head is nothing but the difference between the total heads at the outlet and the inlet of the pump. As you see, we did not use any loss term in the Bernoulli equation. This does not mean that there are no losses inside the pump. There are losses, but they will be included later by considering an overall pump efficiency. In many cases, the elevation difference between the inlet and outlet of a pump is negligibly small, and in many applications the suction and discharge pipes are of the same diameter, resulting in equal average speeds at the inlet and outlet. Under these conditions, the potential energy and the kinetic energy terms of the Bernoulli equation cancel out, resulting in this simplified equation that shows the direct relation between the pump head and the pressure rise the pump creates. Pump head is nothing but the pressure rise across the pump expressed as a head with the units of length. Here it's worth to remember that this equation is valid when the elevation and velocity head differences are negligible, which is not necessarily the case, although seen very commonly. As you may remember from ME305, pump head can be converted into the power delivered to the fluid by multiplying by rho, G, and Q, where Q is the flow rate. According to this equation, pump head can also be defined as the power delivered to the fluid per weight of the fluid flowing through the pump in unit time. This is a more general definition of the pump head with no underlying assumptions. The head generated by a pump depends on the flow rate. The exercise of this slide is about obtaining the relationship between the pump head and the flow rate under idealized conditions. This is a very fundamental relationship, and it is important to know how to obtain it. Detailed solution of this exercise is provided in the solved examples handout. Let's have a look at it. This is the solved examples handout of Chapter 5. The first example is the theoretical head calculation of a centrifugal pump. We see two different views of a simplified sketch of a pump. Here is the R direction and the Z direction. There is also the theta direction, which is not shown. This pump has several curved rectangular blades shown in green color. Blades rotate in the negative theta direction with a constant speed omega. We will perform a control volume analysis. Our control volume, shown with dashed lines, is the circular region that encloses the blades. It has one inlet, shown as 1, and one outlet, shown as 2. Inlet is a circular disk of radius r1, and outlet is a circular disk of radius r2. The control volume has a width of b into the page, which is the same as the width of the rectangular blades. In this idealized analysis, we will use a number of simplifying assumptions. The first one is that there is no axial flow. In other words, the velocity component in the z direction is 0. This makes the problem two-dimensional. The angles beta 1 and beta 2 that the blades make with the inlet and the outlet circles are important design parameters. The solution makes use of conservation of angular momentum and mass. If you were a student in my ME 305 section last semester, you will remember that we have not studied angular momentum conservation. We said that it is mostly used in turbomachinery applications and postponed it to ME 306. And now we will learn and use it. Here you see the Reynolds transport theorem, with capital N being the extensive property and eta being the corresponding intensive property. To study angular momentum conservation, intensive property is selected to be the cross product of the position vector r from the origin and the velocity vector. This makes the extensive property the angular momentum. With these selections, the left-hand side of the Reynolds transport theorem becomes the sum of all the external torques acting on the control volume. Here is the resulting angular momentum conservation equation. To study a pump working at steady state, the first integral on the right-hand side can be dropped. Separating the remaining integral into two, one for the inlet and one for the outlet, the equation takes this form. Our control volume is fixed in space. It's not rotating, but the blades inside it are rotating. It is easier to use three different velocities at the inlet and outlet, forming the shown velocity triangles. Blue arrows show the absolute fluid velocities, seen by an observer fixed at the ground. Absolute velocity is shown with the letter V. Green arrows show the fluid velocities relative to the rotating blades. Relative velocity is shown with the letter W. Red arrows show the linear velocities at the end points of the rotating blades in the theta direction. Letter U is used for them. The relation between these velocities is shown here. This equation is valid both at the inlet and the outlet. We know the direction of the red-colored U vectors. They are tangent to the inlet and outlet circles. Their magnitudes are omega times the inlet radius r1 or the outlet radius r2. As the second simplifying assumption, we will consider the green-colored relative velocity vectors to be tangent to the blades. This corresponds to a flow smoothly entering the control volume and smoothly leaving it. This is a desired condition, but cannot always be achieved in real life, especially when the pump is operating away from its design point. Blue vectors are the summation of the red and the green ones. Their radial and theta components are shown separately in this figure. When we work on the details of the angular momentum equation and combine it with the continuity equation, we get the Euler's turbomachine equation. Please study the details that we skipped here by yourself. Euler's turbomachine equation relates the torque applied to the shaft to the mass flow rate, the inlet and outlet radii of the blades, and the tangential components of absolute velocity at the inlet and the outlet. It is an important equation not only for studying centrifugal pumps, but also for all sorts of turbomachines. It is good to know all the derivational details of it. To continue, we relate the pump power, which is the power necessary to run the pump, to the shaft torque. We also know this relation between the power delivered to the fluid by the pump and the pump head, shown here as H. In this idealized analysis, we will assume that the pump power is equal to the power delivered to the fluid. In other words, we will assume that the pump is working at 100% efficiency. Working on the details, Euler's turbomachine equation can be put into a new form as shown here. The analysis then continues with the third simplification, known as the no inlet swirl condition. To maximize the theoretical pump head, the theta component of the velocity at the inlet is set to 0, meaning that the flow is assumed to be purely radial at the inlet. This is again a desired property which may not be satisfied exactly in real life. With this assumption, the theoretical pump head is obtained as a function of the linear blade tip velocity u2 and the theta component of the absolute velocity v2 theta. What we want to know is how the theoretical pump head varies with the flow rate. The rest of this solution is about getting that relation by using a bit of trigonometry. The final equation that relates pump head to the flow rate is shown here. It can be written in different forms if desired, but this is the form we arrived at. Again, you need to follow the details that we skipped here by yourself. As you see, for a given pump with known dimensions rotating at a certain speed, the H-Q relation is linear. The relation is also sketched as you see. Pump head starts from a maximum possible value and drops linearly with Q. To pump more liquid, we need to sacrifice from the pump head. The actual HQ relation is not linear due to the losses and non-ideal working conditions. The blue curve shown is a typical actual HQ relation of a centrifugal pump. Deviation from the ideal line increases as we go to low and high flow rates. Ideal and actual curves are closest somewhere in between, which is the point where the pump works with maximum efficiency. This is the design point of the pump. Actual HQ relation of a pump is provided by its manufacturer. Pump manufacturers perform experiments to get this relation. Computational fluid dynamics simulations can also be used for this purpose. In the next slide, we have an exercise related to the theoretical pump analysis. It is a problem taken from Munson's book. Its solution is given in the solved examples handout. First, try to solve it by yourself and have a look at its solution if you need help. Other than this one, the handout has one more example related to the theoretical head calculation, but this time for a turbine. Due to several mechanical and flow-related losses, pumps cannot work at 100% efficiency. Pump's efficiency is defined as the ratio of the power delivered to the fluid and the power used by the pump. Power necessary to run the pump, shown with PP, is also called the brake horsepower. This slide provides extra details about various losses that affect a pump's efficiency. We will skip these details this semester. Here are the most important parameters related to the design and operation of a pump. First one is the flow rate, which is also called discharge or capacity. Next one is the pump head. Size of a centrifugal pump is defined by the diameter of its impeller disc. Rotational speed is also important because a pump's HQ relation changes as the rotational speed changes. Last two items are the power consumed by the pump and the efficiency. HQ curve of a pump at a certain rotational speed is known as its fundamental characteristic curve. It is the blue curve shown here. It is also possible to show the efficiency and the pump power curves on the same plot. Typical variations with flow rate are as shown here. Actual curves are different for each pump and depend on how the pump is designed. A pump can operate anywhere on its HQ curve. It is the pumping system in which the pump is used that determines at which point exactly it operates. The two extremes of the HQ curve are known as the shutoff and the free delivery. Both of these are extreme conditions and should be avoided. Pump is not doing any useful work in these conditions. Shutoff corresponds to the maximum possible head that can be delivered by the pump, but this happens at zero flow rate. This condition is obtained when a valve on the discharge side of the pump is closed. The pump cannot create any net flow rate. With zero flow rate, power delivered to the fluid is zero, and the efficiency is also zero. Operating a pump at this condition for an extended period of time can damage it. Free delivery is the other extreme. Here the flow rate is maximized, but the generated head is zero. It is obtained when the discharge side of the pump is not connected to any piping system. In other words, there is no load on the pump. With zero head, no power is delivered to the fluid, and the efficiency is zero. Best efficiency point is the point with the maximum efficiency. It is desired to operate the pump close to this point, which may not be always possible. As we said earlier, the system in which the pump is used determines where it operates. If the system is not suitable for our pump, in other words, if we did not select the proper pump for our system, Or maybe if the system characteristic is not constant but changing with some factors that we cannot control, the pump may work at a point far away from its design point. Operating point of a pump is determined by the intersection of its HQ curve with the system characteristic curve. Let's learn how the system characteristic curve is determined. Consider a simple system with two reservoirs. A pump in between is used to pump water from the suction reservoir to the discharge reservoir. The elevation difference between the free surfaces of the reservoirs is called the total geometric head, and it is shown with HGT. System characteristic is obtained by writing an extended Bernoulli equation between the free surfaces of the reservoirs. This equation has both the pump head H and the head loss of the system HF. In the system shown in the slide, both reservoirs are open to the atmosphere. If also their free surfaces are large with negligible speed, the pump head can be related to the total geometric head and the head loss, as shown here. This is the system characteristic equation, but we need to write it as a function of the flow rate so that we can plot it together with the pump's HQ curve. The flow rate dependency of the system characteristic comes from the head loss, which can be written as the sum of major and minor losses. Suction and discharge pipes of the system create major loss, and all other piping elements such as inlets, outlets, valves, bands, junctions, cross-sectional area changes, etc. create minor losses. After relating the velocity in different parts of the piping system to the flow rate, all other details can be combined into a single parameter shown here as K, resulting in this final head loss equation. Each system has its own K value. As you see, for a given K, the head loss increases with the square of the flow rate. Faster flow experiences more loss. Combining this KQ square relation with the geometric total head, we obtain the system characteristic equation that we need. We can plot it just like the fundamental pump curve. In a sense, this is the demand curve, showing how much head the system requires from the pump at a given flow rate. The required head increases with the flow rate because the losses increase with the flow rate. For the simple two-reservoir system that we are studying, the system characteristic curve can change in two ways. If the total geometric head changes, for example by changing the elevations of the reservoirs or by changing the liquid levels in them, the system curve shifts up or down. If K parameter changes, for example by opening or closing a valve in the system, or by redesigning the routing of the pipes, or by changing the pipe diameters used in the system, or by any other means that affect the losses, the slope of the system curve changes. After determining the system curve, its interaction with the pump's HQ curve gives the operating point of the pump. For the given system, the pump will operate at this point. We want this operating point be close to the best efficiency point. If this is not the case, we can consider using a different pump, or we can try to make modifications in the system to shift the operating point. Here is an example about determining the operating point of a pump in a given system. It is a problem from Munson's book. Its solution is given in the solved examples handout. Please first try to solve it by yourself and have a look at the solution if you need help. This is the end of the third part of the turbomachinery chapter. In the next part, we will study non-dimensional parameters of a pump and similarity of different operating conditions.